Welcome to The Explainer. Today, we're going to pull back the curtain on machine learning and really get into how a machine can actually learn. So, you've heard the term AI thrown around a million times, right? But what does it actually mean? How does a machine go from just, following instructions to truly learning? To get to the bottom of that, we need a plan.
All right, so here's our roadmap. We're going to start with what learning even is in this context. Then we'll build the basic recipe for how it all works. After that, we'll tackle the single biggest challenge in the whole field, and finally, we'll see what makes modern deep learning so incredibly powerful.
Okay, first things first. What does it actually mean for a computer program to learn? And let's just forget the sci-fi images of conscious robots for a minute. In the real world, it's a very specific and surprisingly measurable process. Way back in 1997, a computer scientist named Tom Mitchell gave us this definition, and honestly, it's the bedrock for the entire field. It's not about magic, it's about one thing: measurable improvement. So this whole definition really breaks down into three simple parts. You have a task, T, the specific job, like telling cats from dogs in photos. You give it experience, E, which is just a fancy word for data, tons and tons of labeled pictures. And then you measure its performance, P, which is just how you keep score, like the percentage it gets right. Here's the key. If its performance gets better as it gets more experience, well, then it's officially learning. Okay, so with that idea locked in, it turns out you can build almost any machine learning algorithm using a simple three-part recipe. This is the core engine behind pretty much everything we're going to talk about.
So the recipe has three ingredients. First, the model. You can just think of this as the student making a guess. Second, the cost function. This is like the score on a test. It measures exactly how wrong the guess was. And third, the optimizer. This is the process of studying. It adjusts the model to try and reduce that error. And that creates this constant loop: guess, check, and adjust, over and over again.
But this simple little recipe creates a huge challenge, maybe the most important one in all of machine learning. How do we make sure the model is actually learning a pattern and not just memorizing the answers? This is absolutely critical. A student who just memorizes the practice test is going to bomb the final exam, right? We need a model that can handle questions it has never seen before. In machine learning, that ability to perform well on new, unseen data is called generalization. And that, right there, is the ultimate goal. This whole thing creates this fundamental tug-of-war between two ways to fail. On one side, you've got underfitting, where the model is just too simple, kind of like a student who didn't study at all. On the other side, you've got overfitting, where the model is too complex and it just memorizes the training data, noise and all. It can't handle anything new. So here's a classic case of underfitting. You can clearly see the data has a curve to it, but our model can only draw a straight line. It's just not flexible enough to capture the real relationship there. And then you've got the opposite problem: overfitting. This model is so flexible, it doesn't just learn the pattern, it perfectly weaves through every single training point, including the random noise. This wild curve is going to be terrible at predicting any new data. So the crucial trick is finding that just right balance between being too simple and way too complex. Now, this might make you think, okay, so the goal is to find one master algorithm that works best for everything. But a really famous theorem in machine learning tells us exactly why that's impossible. It's called the no free lunch theorem, and it's a huge reality check. It basically says that if you average performance across every possible problem you could ever imagine, no single learning algorithm is better than any other. A super complex algorithm is, on average, no better than just random guessing. So what's the big takeaway from that? Well, we're not looking for one algorithm to rule them all. The goal is to design models that start with the right assumptions about the kind of data we actually find in the real world.
And this is exactly where deep learning comes in. It's not a universal learner, but it is built on a very powerful and flexible assumption about how the kind of data we care about, like images, sounds, and text, is actually structured. This checkerboard really illustrates the limits of simpler models. A lot of algorithms work locally. They assume a point is similar to its immediate neighbors. But for a repeating pattern like this, that assumption completely fails. To learn the entire checkerboard, a local model would need to see an example in pretty much every single square. Deep learning makes a totally different assumption, that the world is compositional and hierarchical. It assumes complex data is built from a hierarchy of simpler concepts. I mean, think about a face. Pixels form edges, edges form simple shapes like eyes and a nose, and those shapes combine to form a face. Deep learning is designed to learn this hierarchy of features all on its own. This leads to a really cool idea called the manifold hypothesis. Think about it. An image has millions of pixels. creating a space with millions of dimensions. But not every combination of pixels makes a face. All the possible real human faces live on a tiny structured surface within that enormous space. Deep learning is so powerful because it's exceptionally good at finding and understanding the shape of that surface. So how do these deep models actually learn this incredibly complex structure just from data? It all comes down to two key algorithms working together to make millions and millions of tiny adjustments. Okay, the engine driving this is an optimizer called stochastic gradient descent, or SGD. Imagine your error is a giant hilly landscape, and you're trying to find the lowest valley. The gradient is just the direction of the steepest slope right where you're standing. Now, instead of checking the slope of the entire landscape for every step, SGD just looks at the slope of a small, random patch of ground and takes a tiny step downhill. By doing this millions of times with different random patches, it quickly and efficiently finds its way to the bottom. But with millions of settings to tweak, how does the model know which ones to adjust? Well, that's the job of backpropagation. After the model makes a mistake, backpropagation works backward from the error, kind of like a manager figuring out who is responsible at each step of a project. It calculates exactly how much each individual parameter contributed to the mistake and tells it precisely how to adjust to do a little better next time. And there you have it. Machine learning isn't magic. It's a recipe. You define a task, you use a model to guess, you measure its error, and then you use these powerful tools like SGD and backpropagation to improve, millions of times over. But this leaves us with a really fascinating question. If this is all just a sophisticated process of minimizing error, how are these systems now learning to create art, music, and ideas that we've never seen before?